Hi, this is going to be a lecture on complete markets models of consumption smoothing and how they compare to the incomplete markets model that we studied before. The lecture is going to be based on this Jupyter or IPython notebook that I prepared. And it's available on the Google group. I can also send you the notebook if you want to run this. Okay, so we're going to just go through the notebook. We're going to describe two versions of the consumption smoothing models in the spirit of Hall, and I'm going to tell you what that means. So as you'll recall, Hall assumed an exogenous stochastic process for non-financial income and a gross interest rate on one period risk-free debt that equals beta inverse, the reciprocal of the consumer's intertemporal discount factor. That's our basic recall of Hall. Now, as we made use of before, Robert Barrow made an analogous assumption about the risk-free interest rate in his tax smoothing model. And we regarded the tax smoothing model as isomorphic, meaning mathematically having the same structure as Hall's consumption smoothing model. And we're going to play on that. So we're going to maintain Hall and Barrow's assumption here whenever we use the incomplete markets model. But what we're going to do is we're going to extend it to an appropriate counterpart of their assumption when we use a complete markets model. Now, incomplete meant in this context that the only vehicle for borrowing or lending was a risk-free one-period interest rate. A risk-free one-period bond with a constant gross interest rate of beta inverse. What we're going to do is we're going to add more financial instruments here and essentially add as many as is possibly desirable by following the footsteps of Kenneth Arrow. So these notes are going to mostly talk about the consumption smoothing version of the model, but just by changing variables, there's as we've seen before, there's a natural tax smoothing counterpart. And there we just relabel consumption as tax collections and non-financial income as government expenditures. And then we immediately acquire a tax smoothing model. Okay, so we're going to consider two closely related assumptions about the consumer's non-financial income or the government's exogenous expenditures. First is we're going to assume they're governed by a finite state Markov chain. And the second, which we'll talk about briefly, and we've talked about in earlier lectures, is it's going to be described by a linear state space system with a continuous state vector, take on any real values in Rn, that's going to be driven by a Gaussian IID shock process. So we'll mostly focus on the Markov, finite state Markov model, but we'll also talk about the other one briefly. Okay, so I'm going to show you some results, but I want you to keep in mind that what's basically driving these results. So the key determinants are going to be preferences and opportunities. So in terms of preferences, there's going to be a decision maker who wants to maximize some intertemporal objective function that has a preference for smooth paths either of consumption or tax collections. So if somebody wants smoothness, you're going to have to get that half feature if you want to have a tax smoothing or consumption smoothing model. And the second thing is there's going to be some opportunities. So the opportunities are going to be trading opportunities that allow the person that's optimizing to transform possibly a erratic stream into a smoother stream, a stream of income into a stream of consumption, or a stream of government expenditures into a stream of taxes. And the whole theme of this lecture is we're going to describe different opportunity sets. So in the complete markets model, each period, the consumer can buy or sell one period securities, one period ahead state contingent securities. And what these state contingent securities, they look like this. Their payoffs depend on next period's realization of the Markov state. So you buy or sell them now, and their payoffs next period depend entirely on the realization of the Markov state. In the two states change case, there's two such securities. In the end state, there's n such securities. And in a continuous state, there's a continuum of such securities. So these things are commonly called arrow securities, and they're generalizations, as you'll see, of the arrow-Hicks securities that we talked about earlier. In the incomplete markets version of the model, the consumer each period can buy and sell only one security each period. So there's vastly more securities with the complete markets case, and that's why it's called complete markets. Okay, well, as usual in these notebooks, we give you some code because we're going to compute some things in Python. So here goes. So we're going to first talk about the finite state Markov income process for a while. So in this version, in the simple version, we're just going to assume income follows a two-state Markov process, high and low, and there's going to be a probability matrix, a transition matrix P, and the as usual, the ijth entry is the probability that you transit from state SI bar or I today to state SJ tomorrow. So for us, this is going to be a two by two matrix. It's going to look like, say, like this: 0.5, 0.5, 0.1, 0.9. That would be an example. So this is today. Here's today. The rows are today. The columns are tomorrow. The columns are tomorrow. And what the consumer is going to care about is the expected value of a discounted stream of utilities. And the utility functions are going to be curved. So they're going to have u prime greater than 0 and u prime prime negative. And for the most part, we're going to use, as an example of that, we could just use quadratic utility function, which looks like this. There's a bliss point gamma, and we're going to think that we're in this region where we have positive first derivatives and negative second derivatives. So there's u of c. Looks like that. Okay, again, we can get the tax smoothing model if we just set consumption equal to taxes and governing expenditures equal to y. That's the isomorphism. Okay, so what we want to watch in these models, we want to watch two things. How smooth is consumption? So how smooth is consumption both across time and across Markov states? And then how the consumer chooses to make his levels of consumption and indebtedness behave over time and across states. So we want to watch how consumption looks across states and how debt looks across states. So that's where we're going. Okay. Okay. So let's go with the complete markets model, which is the new one. So at each date t, the consumer is going to trade one period ahead arrow securities. So we're going to assume that the price of these securities is exogenous to the consumer. And exogenous, what that means, just to remind you, it means that the decision maker takes them as given and isn't affected by his decision. So we're going to have to make up those. So this is a key little remark. In Markov state ST at time t, 1 unit of consumption next period in state ST plus 1 costs Q of ST plus 1 given ST, units of time t consumption goods. So focus on that. Q of ST plus 1 ST, let's say it's the price, let's say it's raining today. It's the price of 1 unit of consumption if it rains tomorrow. Or it's, if it's not raining today, it's the price of 1 unit of consumption when it's not raining today of whatever state it's in tomorrow. And there's going to be as many of these prices as there are realizations of this state. That's where we're going. So at time t equals 0, the consumer is going to start with an inherited level of debt. That's really due at time 0. And they're in units of time 0 consumption goods. So we're going to have a sequence of budget constraints for the consumer each period. This is every period. He comes into what does he come into the period with? Well, he comes into the period with Y, but then what he does is he sells a bunch of these arrow securities. He promises to pay when the state is in ST plus 1, and he promises to pay, next period he promises to pay such and such amount when the state is in state 1, in state 2, and state 3, given today's state. He promises to pay that, and what does he get for that? He gets price times quantity. So these are the resources that he acquires through sales of arrow securities. And he adds that's what he gets today. If these B's are positive, he's borrowing tomorrow. If the B's are negative, he's lending tomorrow. So positive means, you could say borrowing, he's going to have to pay tomorrow. He's borrowing. State contingent borrowing, and this means lending. But the securities that he's using is risky. It may or may not pay off. So those are his total resources this period. And what does he allocate them? Well, first he has to pay off whatever debt's due, if that's positive, and then he gets to consume. That's his budget constraint. So this is all summarized here. So now we have to say, what are we going to assume about these prices? So remember, Hall assumed that the gross interest rate was equal to beta inverse. Or he assumed that these arrow security prices, his arrow security price was just beta, because he only had one arrow Hicks price. Well, what we're going to just assume is, since there's a whole bunch of states, we're going to assume that these arrow security prices are beta, representing discount, times probability. So this is the natural analog in several senses. Remember, Hall said you get less today when you promise something tomorrow. By what? The consumer's discount factor, beta. That's what he assumed. So Hall only had one state, so this PIJ wasn't there, or it was equal to 1. So what we're doing, notice what we're doing. We're weighting these. If a state is not very likely, it's not going to cost very much to promise to pay something in that state. If the state is very likely, these prices are going to be high. That's the way this goes. And to see this, we'll notice that at time today, state I, if we're in Markov state I, the implied price of a risk-free claim on 1 unit of consumption tomorrow is this. That's the price of a claim. And why do we say that is, well, what is that? How do we get a risk-free claim tomorrow? What we have to do is we have to buy this in every state tomorrow. This is equal to this. The way we get something risk-free, we get it for sure, is we have to purchase that claim, a claim on that good in every state. So this is why I say this is the analog of Hall's assumption. We're going to use it, or Barrow's assumption. So first order conditions for the consumer's problem are, here they are. So you could check out if you maximize the first order conditions to maximize the expected utility subject to the sequence of budget constraints. It's this. So equate the ratio of the marginal utility times the probabilities to the arrow securities prices. It's a key equation. So under our assumption, if you stare at this about securities prices, that naturally implies that consumption, look at this, consumption is equal to CT every period. And that tells you immediately that consumption is equal to a constant. It's equal to a constant. So these marginal conditions, look what we did. We took this. And we just substituted in our equation for the arrow securities prices. And now I'm going to be fancy here. Watch this. So now what we do is this cancels this cancels this. So we get this is equal. So we get U prime CT plus 1 over U prime CT is equal to 1, which says that the marginal utility of consumption is constant. But that means consumption is constant. So there's some fixed value of C that is going to be coming out of this problem. So with complete, we immediately have a complete consumption smoothing, more than we did with incomplete markets. And now all we have to do is to figure out what the securities trades are that support that. So to do that now, we're going to make a guess. We're going to make the guess that when a consumer is in a particular Markov state, he's going to have a certain indebtedness because he chose that the previous period. Come back to that. So we're going to guess that the amount borrowed today depends only on tomorrow's Markov state. So we're kind of exploiting the Markov. We're using two things: the Markov structure, and there's so many securities that we can make this fit together. So we're going to make that guess, and so now we're going to call these. Notice what we're going to call these. We're going to make this guess. So we're going to call B of SJ. That's tomorrow's state. How much you're going to end up wanting to borrow tomorrow, given your state today. And notice, I've assumed that this does not depend on SI, today's state. It just depends on tomorrow's state. Something a little subtle going on here. We're going to make this fit together. This is the kind of thing that Arrow saw in his very brilliant paper. So to determine C bar, all we're going to do is we're going to write down the budget constraints. So now with this assumption, the budget constraints, there's only they're going to be two types depending on the Markov state. When I'm in Markov state 1 today, this is the budget constraint. When I'm in Markov state 2 today, this is the budget constraint. So I just take this assumption and I substitute into the earlier budget constraints, and I get these two equations. So if you stare at those, I can just rearrange those. Those are two equations in two unknowns. the levels of B if I knew C bar, which I don't know yet. Okay, so this is where I've gotten so far. And what I don't know, I've got two equations so far. And I've got three unknowns. I've got B S1, B S2, and C bar. I don't know C bar yet. I don't know any of these, but I know they're linked by this. So now we're going to make the killer assumption. We're going to assume at time t equals 0, B0 is the debt due. So we're going to say that so at time t equals 0, B0 is the debt due, and we're going to assume the Markov state is S1 at that date. What that's going to mean is B0 is going to be B of S1 to make our equations fit. We're going to set B of S1 equals B of Z0. Now, here's our equation system. Now we have three equations and three unknowns. And now we're in business. So with that, we can solve these equations. We can solve all three, and the details of how to do that are there. So now, all of this gives us something striking. The calculations show that in the complete markets version of the model, the consumer makes consumption perfectly constant across time and Markov states. And the second thing is the consumer's debt neither accumulates, decumulates, nor drifts. All it does is it switches between two values, B of S1 equals B0, where you started, and B of S2, which we solved for. So that's the way this goes. So now we're going to show you a Python code, which is easy to write, and we're just going to simulate. Okay, so here's what happens. Here's the Python code. You'll see how short it is. Python code is going to actually look a lot like those equations. We're going to generate a function. The input to the function is beta, p, y, and b0. What else could it be? We're assuming quadratic preferences, but we actually don't even have to assume that because we know that the solution is going to be CT equals C bar. So these are just versions of the equations that we have, and what we're going to spit out is we're going to solve for C bar, B1, and B2. That's what this little program does. Okay, so let's see what it looks like. We're going to test the program, generate some things. But before I do that, that's that program. I'll show you what things look like. We're going to compare that with the version, the Markov version of the one period risk-free debt only. So in the Holland version of the model, the budget constraint, there was only one security, it was risk-free, and the budget constraint became this. And the optimum conditions became this. The consumption was a random walk. Another way to say that is ET of CT plus 1 was equal to CT. It wasn't constant. It was moving around. And what we also found that was that debt also moved around. And these are just repeats of some of the formulas that we had before. I'll let you read this. We basically, we used the budget constraint to get a formula for debt, took conditional expectations. We solved for C, and we got an expression for government debt. Okay, and these little calculations show you how to do it. So, in summary, in our outcomes, contrast to the outcomes in the complete markets model, in the incomplete markets model, consumption's a random walk. And the government debt is going to drift. It now does drift upward in response to low realizations of non-financial income, and drifts downward over time in response to high realizations of non-financial income. And I'll leave it to you to translate these statements into tax collections. Tax collections are a random walk. Government debt drifts upward or drifts downward. And it has a random walk-like component embedded in it. Okay, so here we also have some Python code for the incomplete markets model. That's how you'll see it's very short. So you could actually read this code in and do some experimentation if you wanted to. Okay, so what we're going to do is we're going to take the same, we're going to generate paths of consumption and income, take exactly the same path of income. We're going to freeze the path of income. It'll be a random path that we get from simulating our Markov chain. And then we're going to compare the outcomes in the complete and the incomplete markets version of this. So here's a little code that's going to do this. I'm going to plot this. So and so here's our code. Okay, so here's our key plot, which is on the left, and it's consumption and debt on the right. So the green line on the left is depicting the complete markets consumption allocation, and the little dotted shaded lines are our consumption. Our non-financial income, which you'll see flips between two Markov states. It flips between 15 and 20, with probabilities given by the matrix P that is up above, which I'll let you go back and look at with the Python. And you'll see here's a run of good luck, high consumption, and during that, consumption gradually grows. Still a random walk. And then there's a string of kind of moderate luck, and then there's more bad luck. So more bad luck than good luck, and what we find is that consumption actually drifts downward. So consumption's following a random walk with incomplete markets. But with complete markets, it's completely smoothed. That's what's going on here. What about the debt paths? Well, here we are. The dark blue line is incomplete markets, and there we have debt drifting. But with complete markets, debt just drifts between two values, high and low, depending on exactly what the Markov income state is. So those are the two key differences. In the graph on the left, you'll notice that the consumption is constant, but it varies with a random walk. Again, the debt oscillates between two values with complete markets, while it drifts. So now we're just going to do something that's very inexpensive. We're just going to relabel the variables, and we're going to get tax smoothing interpretations of the two models. So there's our tax collection paths. Taxes are totally smooth with complete markets because the government has purchased insurance on the private sector, and they have a random walk character, like Barrow said, when there's incomplete markets. And government debt, well, again, it oscillates between two values, in complete markets, and it drifts. Okay. And then what I've done for completeness is, in the last section, we've already generated a linear state space model for the incomplete markets version. We talked about that in earlier meetings. With the complete markets version, I've just done the calculations here. And these are completely analogous to what is done above. I just have to use my linear state space representation. And what I can deduce a nice formula for government debt. And I can get the complete consumption smoothing under complete markets, and then generated a little simulation of this one too for you to look at, which I'll let you look at. Under complete markets, we get complete smoothing. Okay, so I'll just conclude this lecture with kind of the following little remark about this complete market structure. Come back here. So you can ask yourself, in reality, which governs the world? Can governments, when they borrow, can they make the borrowing contingent on the outcome? And in particular, here, the key thing is on the outcome of what the government expenditure process is going to be. Or is, when it borrows, does it borrow in risk-free or non-state contingent form? And that, I urge you to think about that. And I'll just give you one example. If you think about a little out of the box. So if we think broadly about what taxes and our expenditures are, think about the following historical example. During World War I, and I think during World War II, the United States government, before and during the wars, it engaged in the following kind of arrangement. During peacetime, say low government expenditures, the government provided subsidies to things like railroads and merchant marine, ships that carried goods, usually in peacetime, or ships that went over the ocean. So the government would provide subsidies to those. But then the understanding, and this happened in the event, is during wartime, the government would nationalize those either ships or railroads, and they would be pressed into government service, giving the owners much lower returns on their capital. And if you think about this is a kind of state contingent borrowing and lending that looks more like the complete markets arrangement than the incomplete markets arrangement. So if you study the history, there'll be elements of both the complete and the incomplete markets models. And I think the way to think about George Hall's video lecture about callable bonds and some of the things that he talks about in the lecture on the Civil War with the famous 520s, fascinating bond issued by the Union during the Civil War. I think you should be thinking about whether the incomplete or the complete markets model or something in between is a more appropriate one to think about them. So this is going to conclude this lecture. Thanks.